Alright, so what we're going to do in the rest of this video is just look at the toughest problems that we dealt with in 6.1. The problems that we got wrong the most, the problems that gave us the most pause, just the toughest problems that I could find. And I selected just a couple, just a few from each of these lessons so that we can really dive into it and see which ones we really need to focus on as we prepare. So if you're dealing with a certain problem and you're like, I need to make sure I understand this particular kind of problem, feel free to jump to that spot of this lesson so you can really understand how to digest and take apart each of these problems. Okay, let's look at 6.1, starting in question 3. It says, let Q equal 3, 4, and S equal 2, negative 7. We need to find the component form and the magnitude of the vector 3QS. Okay, so there's a lot of things that are happening here. If you're ever confused, it never hurts. It doesn't ever hurt to just start by drawing a graph. That's always a good way to start. If you're just, you can kind of get a visual of what's going on. At least that's what I always like to do. It really helps me kind of get a handle on what's happening, what the problem is even saying. Okay, so let's say that Q. Let's make that a green dot. Let's say that's 3, 4. So I'll go 3 to the right and 4 up. That gets me up here. And let's say S is 2, negative 7. So go 2 to the right and 7 down. 1, 2, 3, 4, 5, 6, 2, 7. Okay. So our vector then looks something like, let's say that's, oh yeah, let's make S this blue dot, and let's say QS. Let's make just QS. Let's call that, let's make that a red line. Not 3QS, let's just make it QS. So this is QS, right? Just like that. Oh, this is supposed to be blue. There we go. So blue S, green Q, red QS. That's QS right there. Now we need to find that in component form. Let's make that a light blue, teal. Let's find the component form in teal. Okay, so the component form, as you remember, it starts from the origin. It starts from 0, 0. So I need to take that starting point of our vector and move it down to 0. So to do that, I'll need to go down 3. Or sorry, I need to go down 4 from this green dot, and I need to go to the left 3 from the green dot. So whatever I do to that top part, I have to do to the bottom as well. So I can move everything down 4 and everything to the left 3 to make it the same vector. Because a vector, all it is direction, magnitude. I can put it wherever I want to on the graph. As long as it's got the same direction, the same magnitude, it's the same vector. At least as far as math is concerned. Physics might be a little different. But this is all we have to do. We're going to take this and we're going to put it to the green dot is now in the origin. Move it down 4 and left 3. But that means that S will have to go down 4 and the left 3. Oh man, I hope that I can even fit this on the page. Left 3. So that brings us there. 1, 2, let's see, 1, 2, 3, let's see, 1, 2, 3, 4. That's where that would go. Okay, and let's make our new component form. We said it's teal, so we'll make a teal line all the way down there. Okay, so let's kind of see what this component form was. How would we write this component form? Well, we'd say that endpoint, wherever that endpoint is, we would say that we would put that in greater than and less than signs, and that would be the component form. So this would equal less than, greater than, comma, and whatever that endpoint is, this endpoint down here, that would be the component form. Actually, I'm just all over the place. This is not the component form QS. We're going to find this is the component form. Well, it's the same thing. It's the same thing. If you make component form of, I hope I'm not confusing you. Either way, this is the component form of QS. It's the component form of the red QS. The blue line is the component form of the red QS. So that gives us, let's see, if we started at 2, negative 7, we went left 3, that makes it start at negative 1, because 2 minus 3 is minus 1. We can say that an x value. We've got an x value of minus 1, and that lines up down there. And then as far as the y value of that point, let's see, that is 7. That is negative 7 minus 4. We went 4 down from negative 7. So So that gives us negative 11. This is the points -1, -11. So negative 11. So that's the component form. Okay, so if QS equals -1, -11, because this is the component form. The component form, that's going to confuse you. if this component form is -1, -11, I want to find 3 times QS. So I would say that is, let's use black. 3 times -1, -11 is 3QS. So that gives us -3, -33, which is our answer right here. Okay, so that's how you find the component form. Now we need to find the magnitude. The magnitude is relatively straightforward compared to finding the component form. All we have to do is just use that modified quadratic formula. Not the quadratic form. We're going to use the modified Pythagorean theorem. Pythagorean theorem for this, if you want to draw it all out, this is A, B, and the hypotenuse is C. A squared plus B squared equals C squared. In other words, but all we have to find out is C. So C, or the hypotenuse, the magnitude, the hypotenuse, which is the magnitude, is the square roots of, let's see, -1 squared, -1 squared, plus -11 squared. Okay, so -1 squared is 1, so we get the square root of 1 plus 11 squared, so 11 times 11, which is 121. So we get 122, so we get the square root equals the square root of 122. And so that's the square root of the component form. Remember, that's the square root of the component form. But if we find the square root of 3 times q times s, we would find 3 times this. This would be 3 times the square root of 122. And so that'd be our answer. If that's confusing, another way of thinking about it is if the component form is negative, if the component form of -3, -33, this vector is 3QS. If this is 3QS, we can do the same thing with this. We can say the hypotenuse, let's change color so it's clear we're doing something different. This becomes the hypotenuse equals the square root of -3 squared plus -33 squared. And if you were to work that out, let's see, that'd be 9 plus, what's the square root of, what is 33 squared? I don't even know. Let's pull the calculator for that one, because that's just 1089. Yeah, I don't know. I couldn't figure that out in my head in 5 seconds. So that gives us 9 plus 1089. Then we add those together, plus 9, which gives us 1098. And then we try to pull numbers out, and so that we can pull out, say, well, in this case, we can pull out a 3. You can see that all the numbers add up to 18, which is divisible by 3. So that means this is divisible by 3. If you divide it by 3, that's one of the factors. That's 366. You can divide that by 3 again. That gives us 122. And that's, I think, we could divide that by 2. So right now I'm trying to actually, if you're curious as to what I'm doing, I'm making a factoring tree in my head. 1098 can go to 3, can be split into 3, which is 366, and that can split up into 3 and 122. Divide that by 2, and you can kind of see what the answer is already. This is 2. This gives you 2 and 61, and I think 61 is a prime number. I don't think we can divide that by anything, and so 5, 7. Yeah, I think that's a prime number. So I think from this point that gives us everything we can. We say this is 3 squared. This is the square root of 3 squared times 2 times 61. You can pull the 3 out, which gives you 3 times 2 times 61, or 3 times 122. 3 times the square root of 122. Which is the same thing as before. 2 ways of doing the same thing. You could start with the component form of 3QS, and find that, or you could just start with the component form of QS and then just multiply the answer by 3. Both work. All right. Number 5 asks us, let U equal -1, 3, and V equals 3, 6. Find the component form of the vector -2U minus 2V and sketch a graph. Okay, so we need to find -2U minus 2V. So we're going to start off by just finding we're going to start off from finding -2U. What is -2U? -2U would be -2 times -1, 3. Be -2 times -1, 3. That gives us, that equals 2, -6. And let's see, you could say, well, yeah, let's just go with, for the sake of making it very, very, I suppose, hopefully clearer, let's go 2V, because we're going to subtract 2V. So 2V, that will be in teal. We'll do 2V. 2V equals 2 times 3, 6. Let's make a little partition here. And that gives us, that equals 6, 12. And so if we have -2V, -2U minus 2V, that equals 2, -6 minus 6, 12. And so we just subtract the x's, subtract the y's, we will get -4. That equals -4. Subtract the x's, subtract the y's, you get -18. And that is our answer, as you can see up here. Okay, now we need to actually find the graph. Sketch a graph of what we're doing here. Okay, so if you want to try to find -2U, we found that -2U is oh, they actually graphed -2V. Well, we can work with this. So -2U is -1, -3. So we're going to find a graph with -1, -3. So this has -1. That looks like it could be. Okay. So let's start with. Oh, actually, let's make a dark blue check mark to say it's got 2U. Well, let's say it's got -2U. This has. Oh yeah, no, never mind. This doesn't have -2U. -2U is -1, 3. This does not have -2U. Because that's -1, 3 would be up here. So that'd be -2U. So that one doesn't have it. This one doesn't have it. Let's see, do any of them actually have it? Oh, I see what they're saying. So they've got, if you have -2U, we are subtracting. Hold on, I need to take a second and think about what's going on here. -2 times 1. What are they asking? Oh. Actually, -2U means we are subtracting negative, we have 2, -6. -2U is 2, -6. So we're going to find where they have 2, -6. So 2U would be 2, -6. That would be this line right here. This is -2U. So that would not be in the first graph. That's not there. So the first, we know A is not correct. B does have -2U, you can see, because it is the correct answer, but it's got 1, 2, 3, 4, 5, 6, and then 2, so this is -2U, that works. C has it, it's got the same thing. D does not have -2U, so we can say that's not it. And then for V, So we've got V is 612. So 612 would be, let's see. Yeah, 612, yeah. So, oh no, because it's negative 2V, looking for negative 2V. So negative 2V would be negative 6, negative 12. So looking for negative 6, negative 12, that gives us, that could be A. A's got that, negative 6, negative 12. B has that. C does not have it, so it's not C. And D does not have it, it's not D. So you can kind of see right from here, the only one that actually works is B. B works with 2U and negative 2U and negative 2B. So that gives us the answer that we're looking for. But you can kind of see that what it took two graphs, it took two vectors, and they found the distance between them, went from one to the next. In other words, they kind of added negative 2U and negative 2B, and to add one vector to another, you go from the first head to the second head, and that gives you the added vector. So B is our answer. There, hope that wasn't too confusing. I suppose another way you can think about it is they did negative 2U plus negative 2V, and that would also get you the answer. There's multiple ways to write this problem and to solve this problem, and I'm surprised I went with that route. But it is what it is, and I suppose I've confused you more than helped you. I hope not. So let's move on. All right, question 9. We have an airplane is flying on a bearing of 294 degrees at 520 miles per hour. We need to find the component form of the velocity of the airplane. This one can be a particularly tricky problem, especially because it's got a lot of words. So if you're ever confused, it's never a bad idea to try to draw a picture to see what is happening in the picture and to see what's happening on the graph, or just try to make sense of what these words are saying. So let's try to graph the speed and direction of this thing. Now we can't, of course, graph this to scale because we don't have 520 blocks in our graph paper, but we can do something approximate. Let's graph the 294 degrees first. This is 90, 180, 270, 294 is roughly there. Okay. So we'll draw that. This is 294 degrees, and let's just say this is 520 miles per hour. Okay, so that brings us to this. We need to find the component form of this vector. Now, finding the component form, remember that means we're looking for this point down here at the bottom. I want to find the component form of that. So we'll take that, and we could actually make a right triangle out of this. And once we've made the right triangle, we can just solve this like a triangle. So we know this is we have an angle on the left, and we've got the opposite side and the adjacent side. We know that sine equals the opposite over the hypotenuse, sine theta. And so we'd say the hypotenuse, not the hypotenuse, equals the hypotenuse times the sine of theta equals the opposite. We know that the cosine of theta equals the adjacent over the hypotenuse. So so h times the cosine of theta equals the adjacent. Okay, and let's see. We know that this point here is this x value, or the adjacent side, and the y value, the opposite side. So this is x, y, which is also the adjacent over the opposite. So if we can find those 2 points, we can figure out what this point is. Or find the 2 values to the opposite and adjacent. We can figure out what this point is. Okay, so let's plug in numbers and just find it out. So the hypotenuse, we know, is 520. So 520 times the sine of, let's say, 294 degrees equals the opposite. And then 520 times the cosine of 294 degrees equals the adjacent. And we'll just pull out a calculator and solve it and figure out what it is. And the previous problem, I found out I used 290 instead of 294, and I was very confused. Make sure you use the right numbers. So, in a version of the problem you will not see, but you can see it. If I plug in 520 times sine 294, make sure you're in the right mode first. If you're in radian mode, this will look really weird and it'll be all off. So you want to be in degree mode. 520 times the sine of 294, that is negative 475.043. So that would be our opposite, negative 475.0. And on the right, we have 520 times the cosine of 294. Our adjacent would be 211.5. Okay, those are our two values. And now we can just take that and plug those in. So if this is the opposite and this is the adjacent, then we can say this point is 211.5 and negative 475.0. Okay. And so our component form is just the exact same thing except in greater than and less than signs. We've got 211.5, negative 475.0. And you'll notice that the numbers that they give you over here are backwards, and I think this is a problem with the actual computations of the program. I think the program just sorted the numbers in least to greatest. This right here is the correct answer, and I think if you put in the correct answer, if you put it in correctly, it'll accept it as the correct answer. I don't think it's looking for an order, whether which one is right or wrong. I think there's just a programming mistake. It's not looking for the correct answer. You could switch X and Y or have X and Y correct, and I think it'll accept both of those as correct. So the point is, if you put in this or this, I think they'll both be labeled as correct, and they only put this one in, this first one, it's swapped this way. I think that the computer program defaulted it to this because it starts with the smallest number and then it goes to the largest number, and it's good to, in a computer's mind, to order things from smallest to largest. So anyway, don't be thrown off too much if you see something like that and you're like, oh, my X and Y is wrong. Why is it wrong? Or why is it off? It's not off. So, all right. In 6.2, we're going to start with question 4. Question 4 starts with find the angle in degrees between V and W. All right. So we have V equals 4 times the cosine of 5 pi over 2 times I, and plus 4 times the sine of 5 pi over 2 times J. And W equals 7 times the cosine of 9 pi over 4 times I, and 7 times the sine of 9 pi over 4 times J. Okay. There's a lot going on here. Let's break down what's happening. We've got I and J. If you understand all the different components, this can actually kind of resolve itself pretty neatly. The I and J, to start off with, are just the X and Y values. They are the rectangular coordinates of this whatever this is. Okay, so if I said like 3I plus 4J, I would draw the points 3, 4. That'd be that right there. That'd be this vector right here. So that'd be that vector. If I had a 3I plus 4J. That's all it's saying. So it's just taking a value and turning it into that. Now, if we're trying to figure out what those values are, well, I, if you want a more rigorous definition, is 1, 0, and because that's X, and then J is 0, 1. And we multiply these values by I and J to get where we're going. Okay, and it says the X value, of this, of V, the X value of all this is 4 times the cosine of 5 pi over 2. So it's saying take the remember cosine is X value. The cosine is the X value of something on the unit circle. So it says take the X value of something on the unit circle and multiply it by 4. That's the X value of our coordinate. And it says over here, take the sine for our Y value, for our Y coordinate. It says take the Y value of which is the sine of something, take the Y value of some angle on the unit circle and multiply that by 4. In essence, we're saying we're going to take an angle and we're going to take a distance, and we're going to plot that, because we're going to, for the x coordinate, we're going to take whatever the x value would be if it were something, if it were a certain angle, and then we're going to multiply that by 4, or multiply that by a certain radius. And then over here on the y value, we're going to take the y value, whatever the y value would be if it were at a certain angle, and we're going to make that radius, that distance, 4. Hope that's not too overwhelming, too confusing. Feel free to go back to if you're terribly lost, feel free to go back to 6.2. I cover that in much more detail. Okay. So, what this is saying, this is actually just, this is a polar form in a sense, in a kind of a manner of speaking, that we're converting back into rectangular form. But if we know the polar form, if we're trying to make a rectangular form of something we know is polar, then we can just graph the polar part. In essence, don't be overwhelmed by this. This is 5 pi over 2. This is our theta for w is 5 pi over 2, and our radius is 4. We can just kind of graph that. So this is pi over 2, pi, 3/2 pi, 2 pi, or 4 pi over 2. This would be 5 pi over 2. Yeah, so 4 pi over 2 plus pi over 2. This is pi over 2. This is 3 pi over 2, 4 pi over 2, 2 pi over 2, 5 pi over 2. Okay, so we got 5 pi over 2, and we got a distance of 4. So 1, 2, 3, 4. So that right here, that is V. That's V. All right, let's find W. W is 9 pi over 4. So let's see. That theta is 9 pi over 4, and its radius is 7. So we'll go 9 pi over 4. So let's see. Let's see. That'd be 4.5 pi over 2. I guess that kind of helps me think of it a little better, because it's okay. So it's between 4 and 5 pi. So that's 4.5 pi over 2. This is 4. This is 4.5 pi. This is 4.5 pi. Okay. So that gives us, let's see, that's the angle there. Then we've got a distance of 7. That's the radius, is 7. Okay, and when it asks us to find the angle between V and W. Okay, so if we've got, let's say, maybe to put this in a cleaner way, this is 10 pi over 4. This is 9 pi over 4. This is 10 pi over 4. This is 9 pi over 4. The difference between these two is that this angle in between is just 1 pi over 4. Well, okay, so the angle between them is pi over 4. So, and pi over 4, as you may know, is 45 degrees. So that's 45 degrees. And if you don't know that, just use the conversion. Multiply by 180 and divide by pi, and that'll get you 45 degrees. Okay. All right, question 6. Find the vector projection of u onto v. Then write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. Remember, we read it backwards, so it's projection of u onto v, not projection of v onto u. So we read it u onto v. The biggest number first, or biggest letter first. Okay, before we get into the formula and the numbers and all that we're dealing with, let's just make sure we understand quickly what vector projection actually is, what we're doing. Okay, so we get to, if we have two vectors, let's say these are our axes. Let's say one vector goes in this direction and one vector goes in that direction. What we're trying to do is kind of cast a shadow from one vector onto another vector, so it creates a right angle. So it's like something like this. So it creates a right angle, something like that, and we're trying to cast a shadow, just like that. That's kind of what we're trying to do. And it'd be the same no matter which way it's tilted. If it was this way and this way, we would create a right angle, and it would look the exact same way. But the point is, we're trying to create this projection, and then find out where that shadow, what the shadow vector actually looks like. this vector here is the vector projection. The conceptual idea of what we're attempting to do is we're trying to find the magnitude of this vector, and then we're going to multiply the magnitude of this vector by the unit vector version of the of v. So if this is u and this is u and this is v, we're trying to find the magnitude of we're trying to find the unit vector of v, and we're going to try to multiply it by the magnitude of u as it's projected onto v. Anyway, if you're the formula for this, and I try to boil this down into an easier formula for these particular problems. This is the formula you can use to solve this problem. Oh, this would be an error there. That's a vector v, and it should just make it much easier than the kind of method I was trying to go through before. If you're confused before, just use this formula. This formula will do. Okay, so and we'll just plug the numbers in, and go, and we'll find that vector. So this is step 1. So we project u onto v, and then we're going to write this as a sum of two orthogonal vectors. We'll start with the projection of u onto v. This is we'll multiply. We'll find the dot product of u and v. So first we find the dot product of u and v. U is 6, 3, and v is negative 7, 1. So we'll find the dot product. This is the dot product of 6, 3, and negative. It's not a comma. It's a multiplication sign. And times negative 7, 1. And we're going to divide that by the magnitude of v squared. So we'll take negative 7, 1, the magnitude of negative 7, 1, we're gonna square that. Okay, the magnitude of v. What is the magnitude of v? Magnitude of v, we can use the Pythagorean theorem for that. This would be the square roots of negative 7 squared plus 1 squared. This gives us the square roots of let's see, 49 plus 1, which is the square root of 50. So we get, we're going to put up down here, the square root of 50 squared. Okay, and we're going to make that, we're going to multiply all that, by v, which is negative 7, 1. Great. Okay, we just simplify this, and we will have the vector projection. So the dot product of 6, 3, and negative 7, 1. You multiply the x's and multiply the y's. That's how you do dot products. So we'll get negative 42 and plus a 3. That's what we're doing. 3 times 1 is 3. 6 times negative 7 is negative 42. We divide all that by negative 50 squared. Negative 50 squared is just 50. And we multiply that by negative 7, 1. Okay, negative 42 plus 3, that's just negative 39. Okay, so if we multiply this through, we get this equals, let's see, negative 39 times negative 7, that'd be negative 39 times negative 7, that gives us 273, gives us 273 over 50 times negative 7, not times, comma, negative 39 over 50. And that's the vector projection. And I should check to make sure our numbers are right. Yep, negative 273 over 50, and then negative 39 over 50. That is the vector projection. So that's step 1. Step 2 says to write u as the sum of two orthogonal vectors. One is which is the vector projection of u onto v. Okay, so let's say we have this vector projection now. We want to write this. We want to write u. We want to write u as the sum of two vectors. One, which is the projection of u onto v. This is the projection of u onto v. And this is the second vector. Let's call this vector b. And so these two vectors added together make up u. This is how vector addition works. You put the tail of one vector on top of the head of another vector, and you put them together, and they'll add up to be, and you draw a line from the tail of the first to the head of the second, and that gets the second. That gets this new vector. Now here's the thing. These two vectors are orthogonal, which means they have a right angle just by their very nature. We don't have to try to make them orthogonal, because of the way we set up vector projection, they're gonna naturally be orthogonal. So if this word orthogonal is confusing you, and you're trying to think of how to make it a right angle, you can kind of forget that. It's gonna be a right angle by default because we designed it so that we designed the vector projection of u and v, so there would be this right angle right here. So it's gonna naturally work out that way. We just gotta figure out what we're gonna say. This here, this vector, this projection of u and v, projection of u onto v, plus some vector b, plus some b, equals u, equals vector u. Okay, and so we just gotta add things up, and we'll get vector u. So vector u, I believe, is 6, 3. So we gotta add, so 273.50 plus some x. Let's just make it this. Let's say it's plus some x, plus some x, and then negative 39/50 plus some y equals the negative 39/50 plus y equals 3. Negative 273/50 plus x equals 6. Let me make sure I'm putting these numbers correctly. Yeah, 6, 3. Okay. So now we're gonna have to use the calculator for this because we're gonna have to get actual fractions, as you can see below. What we're gonna do is we're just gonna run this out as a math problem. This will be 273 over 50 plus x equals 6, and then negative 39 over 50 plus y equals 3. Let's see, 6 is the same thing as 300 over 50. So yeah, 6 times 50 is 300. So this would be 300 over 50. And then if I subtract 273 over 50 from both sides, so I do minus 273 over 50 minus 273 over 50. That gives us x equals 300 minus 273, which should be 27, I believe. 27 over 50. 27 over 50. And then y should be goes the similar route. So 3 is the same thing as 150 over 50. Multiply the 3 by 50, that's 150. And then I subtract negative 39 over 50 from both sides, which means I'm adding 39 over 50 to both sides. So add 39 over 50, add 39 over 50, and y equals, these cancel out, so we get y equals, it'd be 189 over 50. So our final coordinates, our final vector should be 27, or our final vector should be 27 over 50 and 189 over 50. And is that correct? Is that right? Yeah. 27, 50, 189 over 50. And we have our answers. Cool. Number 7. Find the interior angles of the triangle with the given vertices. This problem can look daunting at first. It can look very confusing, but it is just the angle between two vectors a bunch of times. And I guess translating things to make them not just translating vectors so that they become translating vectors a bunch. So let's go ahead and figure out what this is. Let's plot this first so we can get an idea of what's going on, because graphing is never a bad idea. One of these days I'll learn to speak, but apparently that day is not today. What we're attempting to do is graph these numbers. Okay, so we've got negative 7, negative 9. Let's see, 3, 6, 7, 1, 2, 3. Okay, negative 7, negative 9. 7, negative 9. No, just not negative 7. 7, negative 9 is our first point. Our second point is 5, negative 6. Okay, we do 5, negative 6. And I think there's a lot to do at first. You can see this is a little tedious at the beginning. Is it 5, negative 6? It's 5, negative 6. I went the wrong direction. Well, one of these days I'll learn how to do pre-algebra. 1, 2, 3, 4, 5, negative 6. Okay, and but it's a little bit tedious, but I think it'll help give a really good visual of what we're trying to do. So negative 1, 7, negative 1, 1, 2, 3, 4, 5, 6, 7, negative 1, 7. Okay, and this is negative 1, negative 7. That's a negative 7, right? It's not a 7. Yeah, cool. And so we'll just connect these points. So we need to find the angle between these, or the angles of this triangle. So let's try to let's just give you different colors to this angle. So this make this orange angle theta. We'll make a red angle theta, and we'll make a green angle theta. Okay. So if I want to find the green angle theta, here's what I could do. If I was to move the entire triangle up to the origin, or move the point 7, negative 9 up to the origin, I could figure out that point, that green angle. In fact, here's what I could do. I can kind of think of this as some vectors. A vector from 7, 9 to negative 1, negative 7, and a vector from 5, negative 6. Vector from 7, 9 to 5, negative 6. If I can find the angle between these two vectors, then I will have exactly what I'm looking for. But in order to do that, I need to get them in component form. So we're going to get them into component form and then solve for that. We're going to get component form if we kind of push it up to the origin. So we'll push everything up to the origin. In order to do that, we need to add 9 to everything, and we need to subtract 7, add 9 to the y values and subtract 7 from the x values. That gives us a new vector. If I was to copy this, let's say I was to, actually let's get rid of that just for the sake of what I'm trying to do here. I'm going to copy this, and I'm going to paste it. Let's say I'm going to draw a new vector. Draw a new thing. I'm going to paste this triangle. Hope I'm not like boring you at this point. Undo. I want to move it. So I'm going to paste it. I'm going to move it so that negative 7, 9 is actually at the origin right there. Okay. You notice we hit new points. If we add 9 to each of these, we get the new coordinates. If we add 9, we don't get negative 6, we get 3 for the y value. And if we subtract 7, we get a negative 2. Negative 2, 3 for this point. And for this point over here, the left point, instead of negative 1, 7, we subtract 7, so we get negative 8. And we add 9, so that gives us 2, negative 8, 2. Alright, so we have two vectors, and we're trying to find the angles between these vectors in a non-component form, so we can go ahead and just solve for this. Let's do that. So the angle between two vectors, again, this is in 6.2, this formula, I believe. So we have the inverse cosine of the dot product of u and v over the magnitude of vector u times the magnitude of vector v. Okay, so let's call this one vector u. Let's call this one vector v. And we're trying to find the angle between these two vectors. Good. So yeah, will that work? That'll work. Yeah, actually, if you want to make it, let's make it. I think it'll make it even easier if we do it. Oh no. If we make this first one, normally it's the vector v is the second one. So make this first one vector u, I think, and this one vector v. I think that'll do. Yeah. I think so. Okay. Anyway, we'll find out. So let's go ahead and multiply them together. So the dot product, the inverse cosine of the dot product of negative 8, 2, and negative 2, 3 over the magnitude of negative 8, 2. What's the magnitude of negative 8, 2? That would be the cosine. That'd be the square roots. So the magnitude of u equals the square roots of 64 plus 4. So that'd be the square roots of 68. So that'd be, yeah, that would not be a perfect root there. So we have the square root of 68 times, let's see, the vector v. this would be this equals the square roots, the magnitude of vector v. Vector v, that's a vector. Magnitude of vector v would be the square roots of 4 plus 9, would be the square root of 13. So this gives us square root of 68 times the square root of 13. Okay. And when we multiply that all together, trying to find the inverse cosine of all of that. So do the dot products. Let's do the dot product. This will give us 16 times 16 plus 6 multiplied by negative 8, negative 2 gives us 16. 2 and 2 times 3 is 6, which gives us 22. It's time for a break for me. I don't know about you all. And then square root of 68 times the square root of 13 times the square root of 13. Okay, so good work, good there. Now what we can do is we can just plug this into our calculator and get the number. So let's see, second cosine. So that would be 22 divided by, let's see, the square root of 68. It's good to have those parentheses so you know dividing by the whole thing instead of just one bit. Square root of 68 times the square root of 13. That way we're dividing 22 by the whole square root of 68 and 13, not just by one of them. And so that gives us, let's see, which mode are we in? We should be in radian mode for this. We need to be in radian mode when we do this. And that'll give us, no, do we need to be in radian mode? I think we need to be in radian mode. No, I was right the first time. Radian mode is degree mode is fine. Because this actually is a number of degrees. Oh my. This actually is a number of degrees. So degree mode, I'll make a little note up here. We need to be in degree mode. Because even I can forget that. I forget a lot of things, as you probably have noticed. So the green angle, then, the green theta, equals 42.273. Or 42.274. Great. And 42.74 degrees. I think that's what the number that's looking for degrees. We could have put it in radians, but that's not what they wanted. Alright, so we need to find the other two angles now. From here, you could use your trigonometric properties, or you could do the same, or you could use those because you have the magnitude of two sides, and you have an angle. So you can use trigonometry, and not just the right triangle properties, but you can use other properties, such as the law of cosines, the law of sines, to figure out the rest of this. But just for the sake of simplicity, we'll do the exact same thing and solve for a second angle, and from there we can just add them up and do the third one, because the three add together to be 180 degrees. Okay, so the second one, let's try to find the red angle second. If I was to try to find the red angle second, let's see if I can still paste this again. I'm gonna erase this. I don't think I copied anything else since then. If I paste it, there we go. I think I'll just actually I'll paste it right over here, not over here, right over here, right over here. Now, you know what? I want to give us as much real estate as we can have. I want to paste it all the way to the right. I know I feel like I'm a little finicky. It's because I probably am. Okay, and we're going to make our new angle. We're going to make our new, oh man, it's all one color. That'll be fine. It'll be fine. Oh, it's not one color anymore. Great. So we're going to make our new axes. That's going to go straight through that red angle. And we're going to try to figure out the magnitude of that red angle. So our new points now, this is now 0, 0. And we subtracted 5 from the x's, and we are adding 6 to the y's to get that up to 0, 0. So that means this becomes negative 6, comma, let's see, we're adding 6 to be negative 1, negative 6, negative 1. And then down here we have 2, negative 3. Those are our values. Okay, and now we just need to find, those are the component vectors, those are our component vectors, and we just need to find, we just need to plug them in and find the answers. So the magnitude of this vector, let's see this magnitude of this vector, this would be, let's call this one u, this one v. The magnitude of u, the magnitude of vector u, this is vector v, is the square root of 36 plus 1, so the square root of 37, and the magnitude of vector v equals the square root of 4 plus 9, or the square root of 13. Okay, and let's see. Let's move on to the actual formula. So the inverse cosine of, let's see, 37 and, oh yes, the dot product of negative 6, negative 1 times, let's see, that's 2, negative 3, and we're going to put that all that over square root of 37 times the square root of 13. The dot product of those two things, that'd be the inverse cosine of, let's see, negative 6 times 2 is negative 12. Negative 1 times 3 would be a positive 3. So we will put that up top. And then at the bottom, we still have 37 times 15. We have 37 times the root of 13. Okay. So we'll just plug that into our calculator and we'll get the second angle. So we'll do inverse cosine of, let's see, negative 12 plus 3, that's negative 9. So negative 9 divided by, let's see, the square root of 37 times the square root of 13. Yes, the square root of 37. This is going to be a negative number, isn't it? Okay, times the square root of 13. And that gives us, oh, it doesn't give us a negative number. That gives us 114.227. So that gives us theta, the right angle, equals mixture. This is degree mode. It's still, yeah, it's still degree mode. So that gives us 114.227. Once I get down to the bottom of my long cache again. So 114.227, or 228 actually. And so we'll plug those together. So we know that let's see, the green angle, we can kind of go up here to finish this up. So the green angle plus the red angle plus the orange angle equals 180 degrees. Okay, and so we know that the green angle is 42.274. We know the red angle is 114.228 plus the orange angle equals 180 degrees. So if we just subtract those two angles from 180 degrees, we should get the orange one. So we'll subtract 118 degrees minus our answer. Let's see, oh, well, I kind of went somewhere I shouldn't go. Second answer. So that gives us 3.772. Okay. No, it's 180 minus, see how easy it is to make a mistake. That's 100, oh my goodness. Let's do this properly. 180 minus 114.228, and delete that last one. Oh man, this is something. And then I'll take that and subtract from that 42.274. That gives us 113.953. No. That doesn't get us that. We get 65 minus 42.274. I'm normally much better with calculators, I promise you. I think you know this. Ah, my goodness. The orange angle equals 23.498. And we can see that those are basically what we have here. Yeah, 114.228, 23.499, and 42.273. All right, I think for your sake, as well as mine, it's important that we take a break here. Question number 9. Find the x-intercept A and y-intercept B of the line and the coordinates of the point P so that P8, the vector AP is perpendicular to the line 2x minus 3y equals 6 and AP equals 1. Okay, so we have got two sections of this. There's finding the x-intercept A and the y-intercept B, and then we've got of this line 2x minus 3y equals 6, and then we've got to find a perpendicular line, and then we've got to make sure that the vector of a perpendicular line on that is if it starts from A is 1. Okay, a lot of stuff here. Let's just break it down piece by piece. Start with the x-intercept and y-intercept, and let's just work from there. So let's start with the x-intercept and y-intercept. This x-intercept, I hope I graphed that all right. Let's make this good. So this is our x-intercept of this line. Well, let's make sure we draw the line first. Okay. Or we could just graph the. We could not even graph the line. We could just find the intercepts, and then we can graph the line using the intercepts. Let's go ahead and do that. So this would be our line. This will have to be good enough. And we've got 2x minus 3y equals 6. Well, how do you find the intercepts of a line? Well, all you have to do is if you want to find the x-intercepts, remember the x-intercept of a line is the place where it intercepts with the x-axis. It's a place where y equals 0. And for the y-intercept, it's a place where x equals 0. So we'll just plug in x and y equals 0. Accordingly, we'll find out what each other's intercepts are. So if I put in 2 and then 0 for x, I'll find the y-intercept. Minus 3y equals 6, which means that minus 3y equals 6, which means that y equals negative 2. So our y-intercept is negative 2, or more accurately, the point 0, negative 2. So and then for the x-intercept, we'll just plug in 0 for y. So we'll plug in 2 times x minus 3 times 0 equals 6, which gives us 2x equals 6, which means x equals 3. So our x-intercept is 3, 0. So we'll plug that point in over here. So that's 3, 0. That is our x-intercept. And we can just draw a line now and connect those two dots and continue it on. Okay. So if I want to find, so we can go ahead and plug that in as the beginning of our answer here. And so we've got, let's actually label those points. This is the x-intercept, this is point A. And the y-intercept is point B. All right, cool. So we need to let's just look at the answers. We've got 3, 0, and 0, negative 2. Yep, those are our x and y intercepts. Okay, so now we need to use those coordinates of the point. We need to use these coordinates we found, and yeah, the coordinates of the point P. So we need to find a coordinate of a point P so that we create a line perpendicular to this. Essentially, we're trying to get a line that's perpendicular to this line, or maybe more accurately, we're trying to make a vector AP that's perpendicular to this line, AP. So this is some sort of P here, and the magnitude of this is 1. Okay, so we're trying to make something that's perpendicular, that goes in that direction and has a magnitude of 1. Okay, before we get into getting to this point right here, so we've got something that makes a right angle, it's perpendicular, does all that, we need to see, can we make a perpendicular vector at all, even in the component form? And here's how we can do that. There is a way to do that. You think about it, if I was to, let's look at this. If I was to plot this point, let's see, if I was to plot the exact point 3, negative 2, and I was to draw a line through it, just like that, well, maybe better than that, something like this. This line should be perpendicular. It should be perpendicular to the other line. It should be perpendicular to the other line, I think, if I'm drawing that correctly. Yeah, I should be writing 3 and negative 2. That actually doesn't look perpendicular at all. Oh, I still don't have it, don't I? Do I? That's the way. There it is. All right, cool. We'll deal with that. If I drew a line that went the opposite direction, that went instead of because the x-intercepts are 3, negative 2. This kind of works in algebra class a little bit. This is kind of an interest, just a tiny bit in algebra class. But if you draw a point, that is negative 2, or it's just 2, negative 3, and it's 2, negative 3. Now remember, what I did here is I switched the x and y coordinates. Maybe a better way to put it is this: negative 2, 3. If you switch the x and y coordinates, that's probably more what you're looking for. If you switch the x and y coordinates, you get a point that is that's on a line that's perpendicular to the line that you've been creating. So here's that's what we've got. We've got a line that's perpendicular now. Now we need to take this line. So again, there's 1 point. This is 3, 0. This is 3, 0. This is negative 2, 0. This is 0, negative 2. And what we did is we made a line that was yx, and we plugged that in, 0, negative 2, and we made that perpendicular line that way. Okay, so now I've got this perpendicular line. Now we need to find a vector of this line that is of the unit circle, a unit vector. So we can do this by taking this vector specifically, taking the vector 2, 3. So if I was to size this down a bit and take the vector 2, 3, if I was to size this down and divide it by its magnitude, well, then I would have a unit vector in this direction. So that'll work just fine. If I size this down, let me just go ahead and cut down all of this here. If I divide this by its magnitude, I will get a unit vector. Okay. So what is its magnitude? What is its size? Well, we use the distance formula to find it. So we'll say the magnitude of vector 2, 3, magnitude of vector 2, 3, that would be the square roots of, let's see, that'd be 2 squared would be 4, plus 3 squared, which would be 9. So that'd be the square root of 13. Okay, so if I want to find a unit vector, I would divide 2, 3, the component 2, 3 by square root of 13. So that'll give me something like this, something red like this, and that'll get me to the points negative 2 over root 13, and then 3 over root 13. I don't know if you can read that. I'm using really small handwriting right now. Negative 2 root. Can I zoom in to make it easier? That doesn't help at all. Negative 2 root 13, and then 3 over root 13. Okay, so we're almost done here. And so we've got the unit vector. All we need to do is we need to push it over to A, push it to the right to A. So I will add 3 to x, to the x value, so that I can move it to the right to A, and we will have our points. If I add 3 to x, then I will get, let's see, I will get finally, so I'll make this green, or I guess P then becomes, let's see, that'd be negative 2 over root 13 plus 3, because I added 3 to it, so it'll go to the right. I translated it right, and then 3 over square root of 13. And let's check to see if this is the answer they're looking for, because I'm thinking it should be. Yeah, because sometimes, okay, so this is the answer that I have is not the answer they're looking for. They're looking for an answer in the opposite direction. And that's fine. We can find it in the opposite direction. Oh, yeah. So they gave us 2 options here, 3 plus or 3 minus. So I went with the 3. 3 minus square root 2. This one right here. I went with this one, and this one works just fine. So this would be the coordinate of the point P. 3 minus negative 2 over root 13, and then 3 over root 13. This would be that point. That's how that would work. If you can multiply both sides by -1 and get this other one, but that's not what I did. And so both these work, because there's two options. You could have gone the other direction too, and you could have made it go this way, and that would have been the other option that they were looking for. But both of those are acceptable answers. Cool. Great. All right. Next one is question 10. It says Ojemba is sitting on a sled on the side of a hill, inclined at 60 degrees, and the combined weight of Ojemba and the sled is 110 pounds. So what is the magnitude of the force required for Mandisa to keep the sled from sliding down the hill? Okay, let's try to make a picture of this. Again, a picture really helps in this one, because otherwise it can be extremely confusing. And I encourage you to watch this entirely, because this can be a really strange problem. Okay, so Ojemba, he's sliding down a hill. He's on a sled, and he's on a sled that's inclined at 60 degrees, and the combined weight of Ojemba and the sled is 110 pounds. So his full weight downwards is 110 pounds. So he's got a force of 110, and the magnitude. What is the magnitude of the force required for Mandisa to keep the sled from sliding down the hill? Now, it won't be 110, because she is pushing upwards. Mandisa is pushing upwards, and her force is not going to have to be the whole thing. It's because part of it's just downwards, and part of it's leftwards, and she has to just overcome that slanted version of it. Let me try to explain what I'm trying to say. This downward direction needs to be projected onto this over here. You see, what would be the essential idea of the direction she needs to go? What is the essential force that's being pushed down? What is the felt force? Because some of it is the ground is taking, but some of it she is taking, as she's keeping Ojemba from sliding down the hill. Okay, so in order to do this, we have to see. Okay, we have to just calculate a little bit of a few things about this particular I don't know, this scenario. So this scenario goes all the way down. I'm speaking too fast. If I were to draw a dotted line all the way down, I could create a right angle, because this is a straight downward pull. And because of that, I can calculate what this internal angle is inside. The internal angle inside, well, if this is a right triangle and 36 degrees is on one side, then 30 degrees is on the other, is on the internal angle. So if I was to zoom in on this internal triangle that we've got here, we've got this. We've got 30 degrees up here, and we've got 110 downwards, and we need to figure out what this is over here, this x over here. Well, we can just use cosine if you want to. This is essentially, I'm trying to do a reduced version of vector projection. This is a simpler version. We need to find the magnitude of this size here, and we could say, okay, well, it's 110. That'd be to figure out what x is. All we have to do is use the cosine. The cosine of 30 degrees equals x over 110. So 110 cosine 30 degrees equals x. And so we'll just go ahead and plug that in. So we will do 110 cosine 30 degrees. Let's make sure that we're in degrees before doing anything crazy. Yep, we're in degrees. And we get 95.263. So 95.263 equals x. And that's all there is to it. That's our answer. It seems really daunting, but if you can understand what the picture is doing and what's happening in the different elements of the graph, that's all we have to do. It's pretty simple. Well, maybe it's not simple. The hardest part is understanding what the graph looks like and how we can analyze it. But that's a way to visualize the graph. Okay. 6.3. All right, question 3. Match the parametric equation with this graph, identifying the viewing window that seems to have been used. And we get this fancy parametric equation here. Now there seems to have been some confusion a little bit about how to graph things well. So let's make sure, I'm going to walk you through all the different potential mistakes you could be making if things don't come out right. First thing you want to check when you're trying to graph a parametric equation, go to mode, make sure that first of all you're in parametric, par for parametric, and secondly, because the t is given in radians, it goes from 0 to 2 pi, as you'll notice, 0 to 2 pi, we want to make sure that our angle is in radians. So make sure you're in radians and your y variable is parametric. Okay, that's the first thing to do. The second thing to do is go to y equals, and you'll notice we have 2 cosine, we'll just plug everything in, 2 cosine t, and we will cube that. And the second one will be 4 sine t, and we will cube that. And then we will go to the, now before we graph it, when we graph it, you might get something really weird, something like this. And so that's not fully there. Things are kind of strange. You want to make sure you edit the window. The window needs to be correct as well. So if we go back to our window, press the window button, we go make sure that t is from 0 to 2 pi. Right now it says from 0 to 2, so make sure it's 0 to 2 pi. That's not just pi, 2 pi. There we go. T-step is just how fine it is, how refined the measurements are, so it doesn't really matter so much. The x-min, let's say it's -10, just so we can get a full scope of what's going on. The x-max could be 10. The y-min, -10. Y-max, 10. Those are both all good things. And then we'll graph that. Okay, it looks like we have a graph that looks something like this. So we have a diamond shape, and that is our graph. So if you look at the 4 options for a graph, you notice that A is the right one because it has a diamond shape. It has an inverted diamond. And then the next thing we do is figure out what the scale is of this. And so you can kind of see that it ends at -2, that the first left end is at -2, and the right end is at +2. So we know that on this graph it goes from 2 to -2, and we know that, let's see, how the top bound is 4. It's 4 up here, and at the bottom we've got -4. Yeah, it looks like it's at -4. Okay, so we've got -4 at the bottom. What this tells us is that it counts the way that tick marks count. It goes from 1, 2, 3, 4, 5 to -1, -2, -3, -4, -5. Let's see, we have 1, 2, 3, 4, 5, and then -4, -5. Here's what I'm trying to say. This bottom part acts as the x-axis, and this is the y-axis. It looks like the way they're trying to structure it is a little bit weird. And so these are the numbers we're looking for. This is x-min, this is x-max, and this is the step. Or maybe more accurate, maybe more helpfully, is the tick marks. Tick. Okay, so it's asking first, what is the minimum of x? We go from -5, we go from -5 to 5. So it's -5, 5. That 1 means we have a tick mark every single one. So we can do 1, 2, 3, 4, 5. That way, if we were given just this information, we have a tick mark every one, we go from -5 to 5, we can reproduce this graph exactly, just the way it is. So 1. And then the y is the same. We go from -5 to 5. And we have a tick mark every single 1 unit. So it counts by 1. 1, 2, 3, 4, 5. Not 2, 4, 6, 8, 10. So that's what we're looking for with this kind of problem. I hope that's a little bit clearer than before. Good. Question 7. The graph of the parametric equations, x equals 4 minus the absolute value of t, y equals t minus 0.4, -5 is less than or equal to t is less than 5, less than or equal to 5, is given to the right. Find the values of the parameter t that produce the graph to the right in quadrant 1. Okay, so it's asking us specifically to find the values. We're trying to find the values of t that'll get us to produce only this section here, only the stuff that's in quadrant 1. So first, in order to do that, we got to find the limits. We got to find those points where it crosses, these cross points here. And so what are those cross points? You can kind of see the cross points yourself. We have, let's see, we have, this is about 4.5. This is, let's see, that's a little bit more. It's 1, 2, 3, 3.5, roughly there. We want to find these exact values. So we want to find when x equals 0. Let's see. We want to figure out when this x-intercept when x equals 0 and the y-intercept when y equals 0. And then we can find those limits of t. So if I can find when it starts and when it ends, those t values when x equals 0 and y equals 0, I'll find those limits. Let me just make it clear. So x equals, I want to find when x equals 0. So 0 equals 4 minus the absolute value of t. And we will find, and then so we're going to find out when x equals 0 to get to that. And we'll say, so when that happens, we get absolute value of t equals 4, or in other words, t equals plus or minus 4. Okay, so when t is plus or minus 4, that's when we hit the y-axis, when t is plus or minus 4. Okay, so if we know, that makes sense. We can see that. It starts, let's see, so either here t equals plus or minus 4, and down here t equals plus or minus 4. We don't know which one yet. We're going to figure out in a second. But that's when it hits that axis. Let's figure out what y is. Actually, no. Let's solve this. So if t is plus 4, let's figure out what y is. If t was plus 4, we'd have y equals 4 minus 0.4, so it'd be y equals 3.6. So when t equals 4, y equals 3.6, and then x equals 0. So that means this point here is the value. Let's see, that's 0, 3.6 when t equals 4. Which should also have to probably mean that this is something like something else. I mean, this is negative 4.4 or something. This is like 0, negative 4.4, and t equals negative 4. Okay, so we need to start. One of our values is t equals 4. T has to be between 4 and another number. It has to be between 4 and whatever number is over here. Whatever t value is there, that x-intercept. To find the x-intercept, we've got to figure out when y equals 0. So we have 0, if we plug in 0 for y, we get 0 equals t minus 0.4. So if we say, if we just say that t equals, if we just add 0.4 to both sides, we get 0.4 equals t. And so we know, there it is. So when this is t equals 0.4. Great. So we know that the values that t has to be in order for it to produce this graph, that just the first quadrant, it has to be between 0.4 and 4 t. So we'll say 0.4 has to be less than t, which is less than 4. And that's our answer. Great. Okay, let's move on to the next one. A particle moves along a horizontal line, so its position at any time t is given by s of t. We need to write a description of the motion. Okay, so let's start just by graphing this function. S of t equals 0.5 t cubed minus 8t squared plus 3t. Negative 3 is less than or equal to t, which is less than or equal to 7. Okay, we could graph this like a parametric equation. In fact, we could. But it looks like this is deceptively like just a normal function. So we can graph it just like a normal function. So you should just graph it like a normal function. And you can see that if you were to graph, in the previous time we went through this, I graphed both of them and showed they look the exact same. We can do the same thing here, but we just need to make sure. But I want to save you time, so instead I'm just going to graph just the function mode. So we'll go just a function, and we will go y equals 0.5. Instead of t, I'll put x cubed no, not squared. We're going to put x cubed, and make sure I get rid of that. Okay, x cubed, there we go. I hope it doesn't break things. Minus 8x squared. This calculator is sometimes a little bit on the fritz. Plus 3, not x squared. What am I doing? Plus 3x. And yeah. And we just got to make sure that as far as our window goes, we're gonna limit x specifically, so it goes from -3 to 7. So that means it's gonna stretch. We're only gonna see from -3 to 7 because it's gonna stretch the window that way. So we'll see that, and that is our window for x. I can try to condense the y, but that's our x window. Okay, so the particle starts from s of -3. So at x equals -3, we start you can notice it starts from down to the bottom, all the way down there-ish, and then it goes all the way up to somewhere about 0-ish, and then it goes down to a certain value, and then it goes back up. And we can see that. It says, let's see, it says the particle starts at s is -3 for at -50, s of -3 to -54. It starts at -54, and it moves right, or in our case, up, because its position is given by this function. So if we get a positive value, that means it's going to the right instead of up. If it gets a negative value, it means it's going left. So it starts going to the right. It starts going upwards. So it's going upwards, and then it changes direction, and then it moves downwards or leftwards for a certain number of seconds, and then changes again at a certain value, this bottom value, and then goes right, goes upwards, and then it ends at s of 7. Okay, so let's just kind of confirm these values, what these are. Okay, to do this, I'm gonna go ahead and quit this, quit, and we'll just do a bunch of function work here. So I'm gonna start by storing -3 as x, and then I'll just plug in the function 0.5 times x cubed minus 8x squared plus 3x, and we're starting, oh yes, plus 3x, and we're starting with x equals -3. So if I plug that in, we start with -54. Okay, so we start at -3 when x is -3. We start at -54. We start at -54 just like we anticipated here, and then it moves. We notice it moves right. We knew that it moved right, and then we just confirmed this. It moved right. We saw that it moved left, and then it moves right, and then it ends up at a certain position. Okay. And then before we figure out how long it moves right for, we need to figure out when it changes direction. We need to figure out that maximum, this maximum here between -2.5 and 2.5. That maximum there. Okay, so let's find that. We can go to math, and we can choose function max, and so we'll just plug in that function from before, and we will say our variable is, well, let's put in the comma. Remember the comma is right above the 7. So, and then our variables x are low. Let's say it's just -2.5, and our high. Wow, you're in insert mode. Your high is 2.5, and yeah, and it'll give us our maximum is 0.195. So our maximum for x is 0.195. That's what this value is here. This value. It changes direction at x equals 0.195. So if we want to figure out what the value is at that point, we could take that answer 0.195 and store that for x, and then run the function again. And that'll give us 0.144. Okay, that gives us 0.144. Then how long is it from -3? So it starts at -3, and then it goes all the way up to 0.195. That's where it changes direction at 0.195. So what's the difference between 3 and 0.195? Well, that's no problem. We can just say 3 minus 0.195, and that gives us 2 point, no, wait, sorry. Yeah, so we have, excuse me, we have negative 3, and we subtract 0.195, and, or no, we add to it, yeah, because it adds 0.195, because we start at negative 3, then we go to 0, and we go to 0.195, so we go a total of 3.195. No, this is, oh my goodness. There we go. We go a total of 3.195 because we go from we go a total of 3. Let me just kind of rewrite this again. Let me give you the visual, because I think you can see it, and I'm just trying to verbalize it in a way that makes sense, in the word that when it makes sense in my words, it actually comes out in words that make sense to you. And in the math, because sometimes that's something, never mind. From negative 3 to 0 is 3, and from 0 to 1.95 is 0.195. And so total, we went an increase of 3 and then an increase of 0.195. So if you want to kind of think of it that way, we have 3 plus 0.195. And that gives us 3.195. And that's kind of what we're looking for here. Oh my goodness, I hope that wasn't too confusing, but that's what we're looking for. Man, it's really, sometimes it's easy to do a problem, but explaining a problem is really difficult, and I think I didn't explain that well, but I care for your time, and I think you kind of understand the intuition of that, because it's not, that one is a really simple question. I think it's just the difference between from here to, from negative 3 to 0.195. What's the distance? How far do you move? So something as simple as that. Okay, then we move. So we at 0.195, and then after that we move left. We move down for a certain amount of seconds, and then it changes direction again at this value down here. We're gonna figure out where down here it changes direction. To do that, we'll do a minimum function. So we'll go to mode We'll go to math fmin, and we'll plug in the same function as before. So this fmin of that, and then our variable is x, and then our, let's see, what was we started with 0.195. That was our let's just go to 0.2 just to be on the safe side. And then to get this end, we'll do, let's say 5 points, let's say 6. Let's say 6. We're going to find somewhere between here and here, find that minimum. Okay, so we'll say, let's say 6 is the end value that we'll search for a minimum, and we get 5.139, 5.138, 5.139, and so that's the answer there. So it moves reverses direction again at 5.139. Let's try to see if I can explain the same thing again. So we go from 0.195 to 5.139. So that total distance that it moved is 4.944 again, because if we take 5.139 and we subtract the 0.195, we will get 4.994. So it moves, that distance that's moved is from here to here. We subtract the 5 from the 0.195, and we get that 4.994. That's where that number comes from. Okay, so you kind of do this a little bit out of order. Okay, what is the value at 5.319 or 3187? Well, we'll take this value, and we'll store it for x, and we'll just evaluate it. We'll evaluate that function. Let's go back and hit that, and we'll evaluate a negative. If we evaluate the function again, we get negative 30.07. So that's where that number comes from. Okay, and so it starts here, and then it ends at s of 7. So our final spot is s of 7, and it ends right there. And so we've got to figure out where it's ending. What is it ending at? Well, let's see. It ends. Well, it says first of all, how many seconds has it moved for from 5.139 to s of 7? How far has it moved? Well, we'll subtract 7 from 5.139, or subtract 5.139 from 7. Excuse me. 7 minus 5.139, and we'll get 1.861. That's how many seconds that have elapsed to go from t equals 5.139 to 7. And then at s of 7, well, what is it at 7? We'll just do 7 store x. Show that for x. And then we'll run the equation again, and we'll get negative 14. So that's negative 14. And that's the answer. Okay, that's 6.3. All right, 6.4. The rectangular coordinates of point P are negative 2, 9. We're going to use an algebraic method and approximate exact solution values to the calculator when appropriate to find all polar coordinates of P that satisfy the following. 0 is less than theta, which is less than 2 pi. Negative pi is less than or equal to theta, which is less than or equal to pi. And C, 0 is less than theta, which is less than 4 pi. Okay, let's see. So we need to find the polar coordinates that we need to find the polar coordinates of negative 2, 9. If you put this on a graph, you would see negative 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. This would give us this point here, which looks just something generally like that. So if we find the radius and the angle, then we'd be able to find the polar coordinate. There's plenty of ways you can do this. Pretty straightforward way is just by drawing a triangle, and by finding the magnitude. We'll start by finding the magnitude. This is negative 2. This is 9, and we can say the magnitude would be the square roots, the magnitude of v, or the radius would equal the square roots of 2 squared, which is 4, plus 9 squared, which is 81. So this gives us the square root of 85. So that's the first part. So this is the radius. And remember the formula for a polar equation. The polar equation we'll say is the square root of 85. It's the radius times the x coordinate of theta times the cosine of theta, and that equals the x value, and then root 85 times the sine of theta equals the y value. So if I go ahead and solve for theta, then we'll have the angle as well. Okay, so let's see what we have here. We know that that cosine of theta equals we know that cosine of theta root 85 times the cosine of theta would equal not just x, because x is negative 2. So if we plug this in, we'll get, if we sort this out, we'll get the inverse theta equals the inverse cosine. It's not parentheses there. It equals the inverse cosine of negative 2 over the square root of 85. I did that rather quickly, but if you plug it into a calculator, you'll get the inverse cosine of negative 2 divided by the root of square root of 85. And let's see, which value do they want? Do they want in radians or in degrees? They want in radians, because it looks like there's 2 pi in this value, so we'll make sure we're in radians. We're in radians, that's good. And we'll plug this in, and we'll get 1.789, or we could say 1.9. So this equals 1.79 radians. Okay. So that's that. We found out the magnitude is the square root of 85. What is the square root of 85? Let's just start with that. What's the square root of 85? That is 9.219. So we have our radius, our theta. So our radius equals 9.2 let's say it's 9.22. Let's say, yeah, the 9.220, and then our theta equals 1.79 radians. And so that's usually where we'd have to be. That's usually where we land. Now, there's a bunch of different ways to write this. You can, if I add 2 pi, if I rotate the entire circle, I'll still be at the same point in the same direction. So I can keep adding and subtracting 2 pi from theta, and I will get to the same spot. So this is 1.79 plus, not just radians, but it's plus 2 times any number pi radians. That's really what we come up with here. And the other thing you might remember, is if I'm heading this direction and I'm going 5 paces in this direction, I could turn 180 degrees. I could turn a whole pi, and then go back 5 paces, and I'll get to the same spot. So if I did theta equals 1.79 plus pi, I'd be facing the opposite direction, and then I have to go backwards in my radius. So I'll go negative 9.220, and then 1 plus 79 plus theta. And then after that, I could keep adding any number of 2 pi. I could add 2n pi radians. Okay, but what is 1.79 plus pi? 1.79 plus pi equals, let's make sure we get rid of that 8, is 4.931. Let's go ahead and make sure this is 4.931, and or maybe 932, and then we will get so we can add any number of 2 pi's to this. Okay, so the first one says we need to find the values that are between 0 and 2 pi. Okay, so we have 1.79, that's between 0 and 2 pi. 2 pi is about 6.2, 6.28. And so 1.79 is between 0 and 2 pi. 4.932 is also between 0 and 2 pi. So these are actually the values that we're looking for. 4.931 and negative 9.22, and then 9.22 and 1.79. Okay, and then if we want to find it between negative pi and pi, we're trying to find it between negative 3.14 and 3.14. Okay, so I'm just going to add, let's see, I want to get, this one is currently just 1.79. That is between negative 3.14 and 3.14. However, 4.932 is not between negative 3.14 and 3.14. So I need to add or subtract 3 pi to get it in between negative 3.14 to 3.14. I need to get it in that range somewhere. And so I'm right now above that range. I'm at 4.9, so I need to subtract 2 pi to try to get down into that range. So I've got 4.932, and I'll subtract 2 pi. That gets me negative 1.351, and that'll do. So negative 1.351, and that's within the range between negative 3.14 and 3.14. So we'll take that. So we'll say the same value. This is the same value for the first one, and for the second one, we'll just change it from 4 to negative 1.352. That's what we'll do there. Okay. And the third one, we need to find all the coordinates between 0 and 4 pi. Okay, so that's bigger than 0 and 2 pi. This is 0 and 3.1. Oh, sorry, not really 3.4, 6.28. But now we're going from 0 to not even just 6.28, but 4 pi. 4 pi would be 12.566. So 12.566. So we need to find all the values within that range. Okay. So we've got 1.79. We can't subtract 2 pi from that and still get something within the range of 0 to 4 pi, because that'd go below 0. If I also subtract 6.28, that would not be in the range anymore. But I can add to it. I can add 1.79 plus 2 pi. That is 8.073. So I could say our values between 0 to 12.566. I've got 1.79. I've got 8.073. Can I add 2 pi to that again and get something else? I would get 14. That's a bit too high. So these are my two thetas. Here's my two thetas when it is 9.22, and I'm trying to get in the range between 0 and 4 pi. How about if I have negative 9.22? How can I get from between 0 and 2 pi there, 0 and 4 pi there? See, I'm trying to go between 0 and 12.66, or 12.566, and so we will do, let's see, negative 9.22, and we will get, sorry, do 4.932 plus 2 pi, and that gives us 11.215. So we got two values now. We got 4.932 because that's between 0 and 12.566, and 11.215 because that's also between 0 and 12.566. Now, obviously, I couldn't add 2 pi again because that would not work. I guess it's way over the value. So these are our two values over here, 4.932 and 11.215. So over here in our answer, we will put for the positive 9.220, we will put 1.79 and 4.931. The 1.79. Oh wait, no. Sorry, this is a negative. This is for 9.220. We'll do that, and we'll do 8.073. Those are our two values here. Now for the negatives, we put 4.932 and 11.215. So for negative 9.220, we would put 4.930 and 11.215 over there. And those will be our answers. I think it's time for a small break before we finish this up. Great. All right, let's finish up these last few problems here. We have for question number 9, transform the polar equation into equation in rectangular coordinates. Identify and graph the solution. So here's what we're looking for to try to solve this kind of problem. We've got r cosecant theta equals 2, and we need to translate the r and the theta into, cosine, or just into x's and y's. And here's the most major tools you'll probably be using to solve that, or just the tools you have in your tool belts. You got r cosine theta equals x, and r sine theta equals y, and that is out of the trigonometric properties. And then you have x squared plus y squared equals r squared. And if you want to have a few other things, you could say things like, tangent of theta equals y over x. But you don't have to worry about that so much. Really, all we need to focus on are those first 3 options, and that should get you all the way in this, especially in this particular one. It's 99% of the time. And even if not, like, you can still use these to get through it. You can use a modified version of these. You can just work with it to get to your answer. Anyway, so here's what we want to do. We want to just play with this a bit until we can find these combinations so we can make those conversions. So if we have r cosecant theta equals 2, well, cosecant is not cosine or sine or tangent. So we want to change it to something so that it become more like that. Well, what is cosecant? Cosecant is 1 over sine. So we'll say this is r divided by sine theta equals 2. And let's see, we're getting closer here. We're getting much closer. Let's see, sine theta is y. R sine theta is y. So if we can somehow get an r sine theta, then we'd be good to go. Well, here's something we can do. We can multiply the top of the equation, the bottom of this fraction, by r. R times r. And that gives us r squared over r sine theta equals 2. Great. So now we can replace the r sine theta with y. And conveniently, we have an r squared now, which means we can replace the r squared with x squared plus y squared. So this becomes, because x squared plus y squared equals r squared, we can write at the top, x squared plus y squared, because that's what this is. And then we can, on the bottom, we can write r sine theta, that is the same thing as y. So we can just write y equals 2. Great. So I don't like that much color. I'm going to change colors again real fast. I'm going to bring this up here. Let's see. We can multiply both sides of the equation by y, and we will get x squared plus y squared equals 2y. We're making better progress here. You can kind of see we've got an x squared and a y squared. That generally denotes that we have some sort of circle going on. So we want to try to get it back into that elliptical circle-like formula. So here's how we can do that. We could subtract 2y from both sides. Subtract 2y. And we'll get x squared plus y squared minus 2y equals 0. Now here's the problem. We want to have just x squared plus y plus or minus something in order to get to the answer. We don't have this extra 2y here. So to find a way to get rid of that 2y, we need to turn it more and more into like a quadratic equation, because we have a lot of tools at our tool belt to get rid of quadratic equations. In fact, if we turn this into a squared equation, if we turn this into a perfect square, x squared minus 2y plus something, if we turn that into a perfect square, then we could factor it out as a perfect square, and that'd be very, very helpful. So let's go ahead and do that. We have x squared plus, let's see, what's the perfect square of this? We divide by 2, and we multiply. We divide by 2 to start with, and so we get y squared minus 2y plus, and we would find the square of that, which is just, we divide by 2 and square, we get plus 1. So we want to add 1 to both sides, so we'll add 1. If you're confused with what I just did, this is a quick summary. I just did almost mentally completing the square. There's a lot of ways to do completing the square. Feel free to look up any one of the options online. I just did completing the square. This is, in algebra, you probably wondered, why did I learn how to do completing the square? Why were you teaching me all this really weird way of doing it? This is exactly why we learned completing the square. It's for this exact kind of problem. Okay, so we have x squared plus y squared minus 2y plus 1 equals a plus 1, or just 1. I can replace that with 1 so it's less confusing. And let's see. I can factor out y squared minus 2y plus 1 to become that perfect square we try to make. So we get x squared plus, let's see, if I were to factor out y squared minus 2y plus 1, this would be y minus 1 squared equals 1. That is the factored version of y squared minus 2y plus 1. And you can prove it by foiling it, and you'll see that that's what it is. Or if you are good with mentally factoring, that's where we are. And here it is. This is actually the answer we're looking for. X squared plus y minus 1 squared equals 1. This is a translated form of the original of a circle of a circle. X squared plus y squared equals r squared. We've just translated it up 1. And you can tell it's translated up 1 because the y minus 1 means it translated up 1. It's normally, if we would say, I can see your head turning a little bit and thinking, well if we had if normally if we had like y squared, if we had y equals 2x plus 3, and we did, I don't know, if we did y plus 2 equals 2x minus 1 plus 3, that would mean that we moved y up 2, and then we moved x to the right by 1. And you're right, yes, that's exactly what it means. It means we moved y up by 2 and x to the right by 1. But anything in parentheses, anything at all in parentheses like this, that you have to make in parentheses, follows that x rule. It follows that x rule of having to go the opposite of the direction. So since we subtracted 1, we're going to go up 1 to compensate. So that means when we plug in 1 into the equation, 1 for y, it'll act like it's at 0. So that's kind of the rationale that's here. It's a much better description that I gave in a previous lesson. But yeah, if you have more questions, please let me know. I can help try to clear it up. But that's the reason why this is translated up 1, so it's up 1. And the radius is 1, and so it's a unit circle. We just translated up 1. Okay. So that means, oh, that's our answer here. And we need to find the graph that best expresses it. We look at these 4 graphs. Let's see, we need to have a unit circle that's been moved up 1. That's been down by 1, so that's not it. Let's move to the right by 1, not it. Move to the left, right, that's not even moved at all, so that's not it. And this is moved up by 1, so it's A. It's moved up by 1. And C was our answer for the last one. Great, that's question 9. Question 11 says, convert the rectangular equation to polar form. Sketch the graph of the rectangular equation, don't use a grapher, and then support your hand sketch by graphing the polar equation with your grapher. Okay, so we'll take this equation and quickly just break it apart and then see if there's a way we can get it back into a polar form. Remember, same tools as before. So x equals r cosine theta, y equals r sine theta, and then x squared plus y squared equals r squared. These are the tools that we really want to be capitalizing on, because these are our most helpful tools here. Let's go ahead and break apart this x plus 5 squared plus y plus 1 squared equals 26 and see if we can find any tools we can just, any ways we can, any x squareds and y squareds, or just x's and y's we can just turn into r cosine and r sine theta. If we turned x into r cosine theta and y into r sine theta right now, we would end up with a mess of sine and cosine that we could work with, but it would take like an hour. Maybe not an hour, but it would take a long time. We don't want to have to do that. So this is a faster way of doing it than just having to. It's easier to break it apart first, see the whole thing, and then translate it to polar form. So instead of trying to do it at the beginning and then trying to deal with the mess later. Anyway, if that makes no sense, here's what we do. X plus 5 squared, let's just break that apart. That gives us x squared plus 10x plus 25. I just quickly FOILed the x plus 5 squared. And then we'll add to that the FOIL of y plus 1 squared. Y plus 1 squared becomes y squared plus 2y plus 1. And then that equals 26. Equals 26. So again, I just FOILed, this is x plus 5 squared. And this is y plus 1 squared. That's x plus 5, y plus 1. Yep. Okay, here's some things we can notice. So let me take out the blue. X squared plus y squared, that's just r squared. Let's say, let's see, 25 and 1, that becomes 26. And yeah, let's stop there for a second. And then let's just rewrite what we've written. So we've got r squared. Let's see, plus 10x, plus 10x plus 2y, and then we've got plus 26 equals 26. We can subtract 26 from both sides to simplify. And these would cancel out. This becomes 0 on the right side. Okay, great. And we're getting a lot closer here. We've got an r squared, which is to our advantage, and we just got an x and a y. This is much simpler to work with than before. So let's just go ahead and convert this x and y into r cosine theta and r sine theta. So this becomes r squared plus 10r cosine theta plus 2r sine theta equals 0. Okay, I can move because I want to have r on one side and I want to have theta on the other, I can move the second and third term over. So this is r squared equals negative 10r cosine theta plus 2r sine theta. No, not plus, excuse me, that's a minus 2r sine theta. I subtracted it, sine theta. And now we're almost there. We notice that the r's are kind of out of sync here. There's 2 r's on the right that we don't want to have, and there's an r squared that should just be an r. We can divide all of this by r to get rid of that extraneous r. So we divide this by r, divide this by r, divide this by r, divide everything by r, and we get r equals negative 10 r, not negative 10 r, these r's cancel out. These r's cancel. And so we get negative 10 cosine theta minus 2 sine theta. And that is our equation. And let's see, that's, yep, negative 10 cosine theta minus 2 sine theta. then we just need to graph this. So sketching the graph using the rectangular coordinates, you can realize that because it's x plus 5, that means we went to the left 5, and because it's y plus 1, we went down 1, and our radius is the square root of 26. So our radius is the square root of 26, which is about 5. So we can just kind of make a circle that way. So let's start with, if we want to make a circle, try to make a circle, we go, let's see, it says go to left 5. Yeah, left 5 and down 1. So 1, 2, 3, 4, 5, down 1. So it means our origin, or our starting point is here. And our size is going to be just a tad bit over 5. So we're going to go up to 4 and start just a hair over 4, and then over just a hair over the origin, or just the y-axis. And let's see, 1, 2, 3, 4, 5, just a hair over that, and 1, 2, 3, 4, 5, just right there. And we're going to try to make a circle that goes around cleanly, and something like that. So this is a rough sketch of what we're trying to look for, and you can kind of see that if we were to look at you choose a graph from among these, we would say it would probably most approximate, well, it's a circle, so it doesn't approximate D, E, or F, or C. It just looks like either A or B, and it looks like A since it's mostly in the second and third quadrant. So B is our answer there. And then we want to confirm it with a graph of the polar version. This is going to be the exact same graph, except the viewing window is just a little bit weird. If you scrunch up the viewing window, you get the exact same thing. And so you could see from all these viewing windows, B, if you just to compare which one of these looks most like, what does B look most like, and these 6 graphs, well, you'd say it looks most like this one. So you just gotta make sure it looks something like this B in this option. So just to graph it, we'll go to polar mode, and we will, let's see, we will go, yeah, we want to make sure that we are in radians. We are in radians, so that's good. And we will choose our y equals to be, let's see, we want to graph, it says graph the polar equation with the grapher, so we'll do r equals -10 cosine theta, and then minus 2 sine theta. And that gives us, let's see, let's make sure our window is decent. So we got a theta is -2 pi to 2 pi, so that's a pretty wide range. That's good enough. Normally we just need 0 to 2 pi. That would do the job, but this is a little bit overboard and it'll work. We don't need a y min that's from 0 to infinity. We can do from -10 to 10. That looks pretty reasonable. And if we graph that, oh, there we go. There it is. There's our graph, the graph we were looking for. Again, if we could just kind of stretch it out a bit, and in the way of this second equation here, to make it look kind of like the second equation, or we could scrunch it up and make it look like the first one. It's just all in the viewing window. That's all that's really going on there. It's the same thing graphed both times. I don't know why they stretched it out for the second one. I'm not really entirely sure what the rationale was behind that. All right, let's look at the last problem. 6.5, we just have one question here. It's question number 11. It says, draw a graph of the following rose curve. State the smallest theta interval from 0 is less than theta, which is less than or equal to theta, which is less than or equal to k, that will produce a complete graph. Okay, so let's see, we need to draw this graph, and again, all I want you to do is just put it in your graphing calculator. That's it. So we have 5 cosine, let's see, that'd be, I'm in polar mode, just so you know, we're in polar mode. And so if you hit y equals, you can press 5 cosine 2 theta, and that gives you this graph right here. So you can tell that it's not, you can tell immediately it's not graph D, C, B, it is graph A. That's the graph we're looking for. That's what I wanted you to know. And then and then you can see the scale. Let's see what are the dimensions here. The graph itself, it ends at 5 and -5 and goes up to 5 and 5. Yeah, so it goes from this value here. If I was to zoom in a bit to as far as I can go, this is -5. This is 5. This is 5. This is -5. So we say this is 1, 2, 3. This goes all the way up to 6. It goes all the way up to 6. This goes to -6, and this goes to -6. So we'd say, oh wait, it's already got the graph for us. So this is the range, -66 by -66, with a scale of 1 and a y scale of 1. There's tick marks every 1. Okay, the smallest x interval that can produce a complete graph. Here's the quick and easy rule. If this is 2, well, if the number of petals is even, if you got an even number of petals, then it's going to be 2 pi. So even petals, petals, P-E-T-A-L-S. Petals is something else, P-E-D-A-L-S, or something else. Even petals is 2 pi. Odd equals pi. If you're curious as to why, go back to the previous video. I try to explain that in detail as to why that, well, at least in enough detail, so you can kind of get a gist of what's going on there. But that's really all it is. So it's got even petals. It's got 4 petals. So it is 2 pi. 2 pi is our answer. And that's all there is. That's all there is to that. As for 6.6, at the time I'm recording this, the 6.6 actually isn't due yet. So I don't have enough data to actually see which problems you're struggling with. So I don't have much guidance there. But for what it's worth, I hope that you did find with these questions helpful, as helpful as they can be. If you have any questions at all, I am here to help you. If there's a question that is extremely difficult and you're like, I don't get that, I can either help you or I can assure you that's not going to be on the test. Whichever one is appropriate, or maybe both. Just let me know. I am here to help if I can. Thank you all for working so hard. This is I love doing this, and it's an exciting thing to do. I will see you in the next video.